Okay, so last time we talked about heat and how they can be absorbed or released. And so we're going to talk about two more vocabulary words that tell us exactly what object is being, um, has heat being released or absorbed. So the universe is divided into two halves. So the one part is called the system. The system is what we're actually interested in, and then the surrounding is whatever is outside the system. So when we say heat is being released, we're saying heat is being released from the system. So whatever object that is, and then it's being released into the surroundings that is on the outside. Okay, so the system and the surroundings is what makes up the universe. Okay, so we talk about exo being released, like exiting, endo being absorbed. It's entering, it's coming in. So here are some examples about system and surroundings. If you have a hot cup of coffee, this is what we would call our system. Then what would be the surrounding? The surrounding would then be the air around it, right? The air is what surrounds that hot cup of coffee. So what's happening if you leave a hot cup of coffee out on the counter? If you leave it out and you leave it out there and let it do its thing, then what happens? The heat, right, is then exiting out of the coffee, right? It exits, right, into the air. So remember what we talked about last class right here, heat will always flow from whatever's warmer to the cooler object. So because a hot cup of coffee is what's warm, the heat's going to leave into the cooler air. That's what makes your coffee end up cooling down. So the system is then having heat exit. So this would be an exothermic reaction because heat is exiting the system. Now, in this example right here, this is the system. This is a cold can of soda. It says cola. Okay. Then what? The air is then the surrounding, right? So now you got to think what's happening here. If the Coke is what we're interested in, and you leave a really, really cold soda out on the counter, then what happens to that soda? And you're like, it's gonna warm up, right? So the outside air is now warmer than the actual object of interest. So the warm air is now going to, so the heat is then going to enter, right, into the soda, right? So the surrounding air has the air go into the system. So the system is now gaining heat, right? That's why the soda will eventually warm up. So this is an endothermic reaction because heat is entering the system, and the system is the actual Coke can, right? So a couple more examples that I can do here, right? When you have water freeze, right, you got to think, okay, that means it went from a liquid to a solid, right? So the system then is the water itself. The surrounding is going to be the air, okay? So why would it freeze? How does liquid water become ice, right? Where does heat have to go? So heat, so I like to do this side first. So heat is doing what? Is exiting. It's exiting. It's leaving the water, right? And that's what causes it to like freeze up, right? And so this, if it's exiting out and leaving out the water, then you know that this is exothermic, right? It's exiting out. That's how you get water. If water has to cool down, get really cold, how does it get cold? It's because heat has to leave the system. So here, solid wax melt. So this is like, hey, you have like a birthday candle of some kind, and then it starts like melting, right? So let's think. So it becomes solid, then becomes a liquid because it's melting, right? So the wax is the system, and then the air surrounding it, right? It's the surroundings. And so you got to think, why would our wax melt? It melts because it's getting hotter and hotter, right? Like the candle is you know, going. And so heat is then what? Entering, right? Coming in to the wax. So if it's entering into the wax, then you know that it's endothermic. And we're talking about the system, right? We're not really talking about the air. The air is actually doing the exact opposite, right? Because it's the surroundings, right? So the heat from the air is what's going into the system, which is our wax there. Okay, so does everybody understand the difference between endo and exo and system and surroundings? All right, now here's this last thing is this vocabulary word called enthalpy change. Enthalpy change is denoted by the letter H. Once again, it also tells us if energy is being absorbed or released by a system. It's usually measured in kJ or joules. And you know 1 kilojoules is equal to 1,000 joules. Okay, so that J stands for joules. Okay. So if something is endothermic, and you got to think about like now, let's think about chemical reactions. The energy that you're starting with, right? So your reactants, this is what you're starting with, is low. You have like a certain amount of energy. Now, if it's endothermic, right? This endothermic word here means that heat is entering, right? You are gaining heat, and heat is energy. So that means where you end up has to be a lot higher energy. So this is where your products is. This is where you end up. Now, you would think that it's like a straight line across, but in chemistry, there's actually like this weird little hump that needs to be drawn like this. It actually like pushes way up higher than you actually need so that it can like fall down into the right spot. So same thing here on the opposite side. If something is exothermic, right? You know, heat is what? You are losing heat. Remember, heat is just a type of energy. So if you're starting with the type of energy, so here we're starting with a certain amount, right? Reactants, R for reactants, this is where we're starting. Then P, products, you would end up losing energy, right? You end up with less energy. So remember, it's not a straight line. You have to like go up and then come back down. So you have to like jump up to like lose that energy. So it's all about, so don't really focus on where exactly the humps are. Think about where you're starting and your end point. Am I gaining energy or am I losing energy? Okay, so think about it that way. All right, so let's do like a quick summary of all our vocabulary words. So endothermic, energy is being absorbed. You know that. Q is heat and H is enthalpy. Anytime something is endothermic, we denote it with a positive value. So endothermic is definitely absorbed. You see a positive number. So Q is heat, H is enthalpy. So anytime you're trying to break bonds, you need to absorb energy. You need to like muster up all that energy to like break bonds so that you can form new ones, right? So breaking bonds does require you to gain and absorb a lot of energy. If you were to write this in a chemical reaction, the energy will show up in the reactants, which is before the arrow. This means you need that energy before you can actually make anything. So like, for example, here, it tells us that delta H, so enthalpy here, is a positive 32, right? So that means that every time you see that positive, you know you're gaining, absorbing energy. Now, you need this energy in order to start the reaction. So the energy has to be one of the ingredients, right? One of the reactants in order for this to work. So you always put it before the arrow. I usually put it at the very beginning as a sign to me to let me know that, hey, I need this energy or this reaction is not going to go. Okay, like this reaction cannot happen unless I have 92 kilojoules of energy, right? And that's why it's in the front. So then in the exact same fashion here, exothermic then, right? Energy then is being what? Released. How do you denote an exothermic reaction? Is by using a negative number, right? Negative, negative. Remember, Q is just heat, delta H is just enthalpy. You can write that in really quick. Now, after you like break bonds, so you like gain all this energy to break them, and then you form new ones, like you form little friendships and compounds, then when you form these bonds, you actually will release energy because you don't need it anymore. You're not like trying to break anything anymore. Now you're trying to be like nice and sharing, or like doing all that kinds of forming bonds, right? Forming friendships. So you can release energy, release that tension. Okay. Energy is going to appear in the product section, which is after the arrow, because now what you're trying to say is, I don't need this energy anymore. So now it can go away. We can exit out. I don't need it anymore. So when you look here, you can see that the energy is negative. So it's telling you, hey, we are losing energy. We're losing heat, right? Now, when you see it in a chemical reaction, you're not going to see it with a negative number. So here, we're going to see that if I just write energy here, right? This tells me if I see energy after the arrow, I'm losing energy. That's what it's saying. So if you look at this number really quick, this is where a lot of people mess up here, okay? You see that there's no negative here, but where is it located? It's located after the arrow, which means that, hey, I don't need this energy anymore, so it's actually going to go away. I'm going to like put it out into the surroundings because the system doesn't need it anymore. So you don't have to put the negative in a chemical reaction. In a chemical reaction, we always use plus signs, because plus signs doesn't mean like adding. It just means the word like and. Like, so like nitrogen plus hydrogen is going to make ammonia and lose 324 kilojoules. That's what that plus sign means in a reaction. It's just another word for like and. So the location of the number is what's actually more important, right, than anything. It's like, is it before or is it after the arrow? So if it's before the arrow, you know you need that energy in order for it to go. Okay, when it's after the arrow, you are throwing that energy away because you don't need it anymore. All right, and that's it.